Welcome everyone to today's webinar, Optimizing Power and Performance, LTPI and MIPI for Small Footprint FPGAs with Lattice. We're thrilled to have you here as we dive into the possibilities of leveraging Lattice devices and these advanced protocols like LTPI and MIPI for innovative designs. So whether you're an FPGA engineer or a system level designer or just curious about the next wave of protocol innovations, today's session really promises actionable insights and real-world examples to inspire your next project. Before we begin, just some quick housekeeping items to ensure a smooth experience throughout today's webinar. We will have a Q&A at the end of the session, so please do submit your questions through the app at the bottom of your screen. At any time, feel free to type them in, and should you encounter any technical issues, just send a message through the chat and our webinar admin team are here and will help you. So who are Fidus? We were founded in 2001 and we've grown into a very close to 200-person, all North American electronic system design services company. We serve all industries and markets and have 3 brick-and-mortar locations, 2 in Canada and a US home base in Silicon Valley. We've been working with embedded systems and FPGAs since 2002, and it would be safe to say that 80% of our projects have included FPGA content. We're most proudest of our repeat customer rate, with close to 95% of our customers returning year over year with new projects and new business, a real testament to the quality and efficiency of our work in improving their time to market. We have a very strong partner ecosystem with partnerships with AMD, Altera, Lattice Semiconductor, Microchip and Analog Devices, to name a few. As a full services design firm, our professionals and engineers cover a multitude of service disciplines, including FPGA and ASIC design, validation and verification, UVM verification, software, hardware, SI and power integrity design, RF and wireless systems, as well as mechanical and thermal design. We help our customers by supplying some of these skill sets directly or by managing the complete project from start to finish. Now, before we begin, please let me introduce our 2 speakers. Scott Turnbull is the CTO at Fidus, and he's responsible for understanding our client requirements, generating estimates, and leading the advanced tech group here at Fidus. With more than 25 experience in the design services industry and a degree in electrical engineering, Scott brings unmatched creativity and technical leadership to Fidus. Joining Scott is Matt Fransham, Solutions Architect at Fidus. He's a senior FPGA designer with over 15 years of experience in FPGA and embedded software, with expertise spanning broadcast, video compression, and telecom. He's highly skilled in FPGA and system co-design, high-speed interfaces, and UVM verification, with extensive experience using AMD, Altera, and specific to today, Lattice platforms. Now, I will hand it over to Scott to get us started. Over to you.
Thanks, Alicia. Hello, everyone. First off, thanks for joining us for this discussion on LTPI, MIPI, Lattice devices and tools, and how all of this came together in our recent Lattice-based LTPI demonstration. As mentioned, my name is Scott Turnbull, and I'm the CTO at Fidus Systems. I decided that this webinar could be useful to people as they explore the use of LTPI and/or MIPI in their FPGA designs. It is worth mentioning that LTPI is almost solely focused at FPGA platforms, whereas MIPI is extremely common in both FPGA and processor-based implementations. LTPI soft IP is available or becoming available from the large FPGA vendors, and MIPI soft IP is already super common across most manufacturers. MIPI, in fact, has become so common that multiple FPGA vendors have started providing hardened MIPI controllers and interfaces within their chips. For years, Fidus has completed a huge number of MIPI-involved designs and several LTPI-based designs. Our latest LTPI design targeted a Lattice MachXO5-NX FPGA device and was showcased in person and online at Lattice DevCon 2024. I promise to keep this short and informative by starting with the details on LTPI and MIPI before Matt takes you on a deep dive into our LTPI DevCon demonstration and the tools, devices, experience we had when developing the demo. To close out, we'll discuss some thoughts on the use of LTPI for some maybe more atypical applications, Anyways, thanks for joining us. Let's get started. First thing, what is LTPI? Well, LTPI stands for LVDS Tunneling Protocol and Interface. It came out of the Open Compute project and is naturally specified for data center applications that require common connectivity between the secure control module and the host processor module within such systems. Taking a closer look, LTPI makes use of a frame structure that contains different time slots to enable the multiplexing, aka tunneling, of common I/O such as I2C, GPIO, and UART onto a single higher speed bus. This multiplexed approach reduces the number of interconnects between the HPM and the SCM, as well as other cards. Interestingly, the LTPI authors also allotted time slots called the data channel and the OEM channel. The data channel is primarily intended for memory mapped applications. The OEM channel is less defined and allows for significant creativity in the type of information being transferred. Note, LTPI supports two types of GPIOs, normal latency and low latency. Low latency GPIOs are transmitted in every frame, whereas normal latency GPIOs are updated based on the total number of normal latency GPIOs used. As per the standard, LTPI is targeted at FPGA and CPLD implementations. Hence, programmable devices are leading the way for LTPI. Physically, as mentioned, the L in LTPI refers to LVDS, or low voltage differential signaling. Using LVDS enables the system to tunnel the aforementioned low-speed protocols at comparatively high speed. For example, the Lattice MachXO5-NX device and soft IP can support LTPI rates up to 1200 megabits per second. A single LTPI link is constructed of two unidirectional paths, specifically a TX clock and TX data pair, and an RX clock and RX data pair. In summary, LTPI is a high-speed FPGA or CPLD targeted transport of common low-speed management protocols, while also providing some user flexibility to include custom data within that tunnel. With LTPI now defined, let's take a look at MIPI. Years ago, the MIPI Alliance came together and specified various MIPI standards. Both the embedded processor industry and the FPGA industry have widely adopted and supported MIPI technology. MIPI's lightweight, low pin count connectivity, low power, reduced EMI signature, and high throughput capability have made it the de facto interface for video data movement in mobile applications and in a lot of cases embedded systems as well. The MIPI Alliance has defined various protocols and physical layers to be leveraged by mobile devices. Here's a quick snapshot of some of the most common. CSI2, or Camera Serial Interface 2, is the reigning champion protocol of interfacing an image sensor to a host device. The image sensor side utilizes a CSI2 transmitter, or TX, and the processor, or FPGA, leverages the CSI2 receiver, or RX. With gigabits per second of data throughput and an I2C bus for configuration, CSI2 can transfer video of many different color spaces, formats, resolutions, and frame rates. Common interfaces make use of 1, 2, or 4 lanes based on the resolution and frame rate. All major image sensor vendors and all major processor or FPGA vendors have solutions for CSI2. DSI2, or Display Serial Interface 2, is conceptually similar to CSI2, except it targets data transfer between the processor FPGA and the display. These are typically full-color, high-quality video displays and not character displays. MIPI DSI2 is a fairly easy way to incorporate a great-looking display into a relatively low-cost embedded platform. Like CSI, DSI utilizes a single or multi-lane approach depending on the needs of the display. Also like CSI, all major display vendors and all major processor FPGA vendors offer DSI solutions. CSI and DSI all require a physical layer implementation. DPHY, CPHY, and APHY are physical or PHY layers specified by MIPI. DPHY can transfer gigabits per second using SLVS signaling. CPHY leverages 3-level signaling to further increase throughput, and APHY is hyper-focused on transferring data across longer lengths. Think automobile lengths. With regards to FPGAs, DPHY is common across many vendors, and CPHY is slowly emerging. Now that we've discussed some of the high-level technologies involved in our LTPI DevCon demonstration, here's Matt to discuss our implementation, specifically what we did, how we did it, and our lessons learned. Matt, take it away.
Thanks, Scott. So shown here is a high-level block diagram of our full demonstration setup. The objective was to use only off-the-shelf hardware for this project. This included two MachXO5-NX development kits, a Raspberry Pi 3B Plus, 7-inch display, a Raspberry Pi camera module, and Lattice Camera Link and AP Link breakout boards. The two development kits are connected to each other using an LTPI link. The camera module sends video into one dev kit, which packages the video data into LTPI frames and sends the data to the other dev kit. The second dev kit extracts the video data from the LTPI frames and outputs it on the MIPI TX interface to the Raspberry Pi, where it is shown on the display. The Raspberry Pi software is unaware that the camera is connected remotely, and it can function just as if the camera is connected directly to its CSI camera port. A milestone-based design strategy was implemented for this project. This involved proving out subsets of the design individually, building them up to form the final demonstration. We started by working with the LTPI and MIPI cores in isolation using single board setups. Milestone number 1 involved a basic LTPI demonstration where the state of onboard dip switches could be passed over the LTPI link using the GPIO field to control LEDs. Milestone number 2 involved a MIPI RX to MIPI TX loopback, proving out interoperability between the FPGA and the Raspberry Pi. This also showed that the Raspberry Pi could detect the camera even if it wasn't plugged in directly to its CSI camera port. Once these designs were working on their own, they were combined to create the final demonstration. This milestone-based design approach is something that we have applied to multiple projects at Fidus, and we feel like it provides a lot of benefits. It allows us to prioritize the de-risking of major project unknowns, partition a complex design into manageable components that can be built upon, and clearly divide responsibilities and ownership across different team members. In terms of development tools, Lattice Radiant was the main tool used to build our FPGA project, configure and generate IP cores, build FPGA bit files, program the hardware. The simulation wizard within Radiant offered a really fast way to generate a simple test bench and simulation run scripts for our design. The generated test bench could be run using Questa and was easily built upon to create more extensive test cases as our design got bigger. When debugging the design on hardware, the Lattice Reveal Logic Analyzer tool proved to be essential to gain visibility into what was going on within the design. It was simple to add new signals to the analyzer and configure different trigger scenarios. I'll talk now about a few of the design challenges we encountered while working on this project, including the available bandwidth for video on the LTPI link, how to pack the video into an LTPI frame, and clocking considerations for the MIPI and LTPI interfaces. One of the first challenges of this project was determining how much bandwidth was available for video transmission over the LTPI link, and what video encodings and resolutions would work. Using the 600 MHz maximum link speed of the Lattice LTPI IP core, along with DDR, allowed for an effective link speed of 1.2 gigabits per second. At this link speed, the LTPI frame rate works out to 7.5 MHz, or put differently, a new LTPI frame is transmitted every 133 nanoseconds. The GPIO and OEM fields within the LTPI frame were identified as the leading candidates for carrying video data. There are 32 bits reserved for each of these fields in an LTPI frame, and they combine for about 480 megahertz of bandwidth. This bandwidth wouldn't allow for high video resolutions, but lower resolutions such as 640 by 480 were determined to be possible. The objective was to maximize the frame rate that could be carried and to try to achieve 60 frames per second. To do this, the bits per pixel would need to be kept to a minimum. RAW 10 encoding is the format natively output by the Raspberry Pi camera module and uses 10 bits per pixel. This was determined to be a better option than something like 8-bit RGB, which uses 24 bits per pixel. With RAW 10 encoding and a frame rate of 60 Hz, the video data would require 184 megahertz of bandwidth, and for 30 Hertz frame rate, it'd be half of that, 92 megahertz. These were deemed to be appropriate targets, and we didn't want to be too close to the theoretical maximum because that could lead to more internal buffering requirements in the FPGA to handle burstiness of video data. Driving video data over the OEM interface of the LTPI core was a different use case than how that interface would typically be used. The OEM pins on the LTPI core are defined as in-outs, meaning that they are bidirectional and need to be connected straight to FPGA pins. The conventional use case for the OEM interface would involve driving it to or from a source external to the FPGA. In the case of this demonstration, we ideally would have been able to drive the OEM interface directly from logic in the FPGA. However, the Versa connectors on the MachXO5-NX board offered a way to work around this issue. The video data was driven out of the FPGA to the Versa connectors and then looped back to pins assigned to the OEM interface of the LTPI core using simple jumpers. This solution ended up working out well, but the limitations encountered here for the OEM interface should be kept in mind if it is being used for other applications. When doing initial LTPI link integrity checks between dev kits, it was found that some data was being dropped. This was determined to be caused by lack of synchronization between the LTPI clocks across the two boards. In order to work around this issue, it was necessary to use the LTPI clock provided by the SCM to drive the PLL in the HPM, as shown in the diagram on this slide. Once the synchronization mechanism was implemented, no data loss was seen at all across the LTPI link. The other issue encountered with clocking was related to clocks driving the DDR outputs of the LTPI and MIPI TX cores. There are only two PLLs in the FPGA device used for this demonstration. And only one of them can drive the DDR I/O banks used for the LTPI and MIPI transmission. This meant that the MIPI TX and LTPI interfaces needed to share a common reference clock. This didn't cause major issues for our particular demo, but it does impose a constraint that the LTPI and MIPI line rates cannot be completely independent of each other. As we mentioned previously, we demonstrated this video over LTPI demo at the Lattice Developers Conference back in December. As part of the conference, one of our directors of business development, Chris Miller, filmed a video where he demonstrated our setup in action. We're going to show part of that video now, and then we'll bring Scott back for some final thoughts.
So now what I'll do is I will show you and describe our demo. So here we have a Raspberry Pi MIPI video camera connected to the first MachXO5 demo board, which we call the HPM, the host processor module. The host processor module is now connected through the LTPI connection. This is send and receive to the second MachXO5 board, which we call the SCM, the secure control module. Now the secure control module is connected via MIPI to our Raspberry Pi display. So essentially what we're demonstrating is that you can send high-speed video over the LTPI communication protocol in addition to your common low-speed housekeeping signals, such as GPIO. And you can demonstrate here how the lights are lighting up using that. LTPI video going one way, general purpose I/O going the other way. And that's our demonstration. Thank you.
Thanks, guys, for that detailed look. Now, to finish up, I just want to share some last thoughts with you about LTPI. As Matt described, we made use of the OEM channel and the GPIOs in an unorthodox way to carry video. Admittedly, while video transfer is probably not a key need or focus within the data center environment that OCP conceived LTPI for, the message is LTPI leaves a lot of bandwidth on the table for creative uses. The OEM channel is very open, whereas the data channel is more prescriptive because of the way that it was specifically designed for memory mapped applications and the way that IP vendors recognized this intent and implemented it as such. Although designed for inter-board communications, we can see uses for it in intra-board communications. For example, most boards that contain multiple FPGAs have high-speed links connecting them. With the I2C GPIO and UART, tunneling of LTPI, some applications might want to leverage LTPI to simply extend a software-based control plane from, say, an SoC FPGA to another onboard FPGA. Boom, GPIO, I2C, and UART pins on the master device. Anyways, I hope you have found this information useful. Please see the links included throughout this presentation for additional information on LTPI and MIPI. Thanks for your time. Alicia, over to you.
Optimizing power and performance. Okay, hello everybody. Thank you very much for that presentation there, Scott and Matt. I see Matt and Scott's probably just turning on his video. So just a quick reminder to everybody, I've already seen some questions come through, but if you wouldn't mind popping it into the Q&A, we will attempt to answer your questions live. So the first question I have here is, to either of you, if you could answer it, can LTPI be adapted for applications outside of data center SEM systems, such as automation or aerospace?
Yeah, so I'll grab that one. So yeah, totally. And it was funny, right? When we were looking at LTPI for the first time, we're like, oh, this could be useful in so many other applications. Anywhere that you want to multiplex a bunch of low-speed control signals and save yourself a bunch of either backplane interconnects or board-level interconnects, and just rely on that one LVDS link, we could see it being used for that. I also like the fact that it can basically be used to extend like an SoC type I2C bus from a software perspective all the way across a bunch of devices. And for software, it just looks like a single I2C or UART at the system level. So I like that level of abstraction that the hardware can provide.
Excellent. Thanks, Scott. Anything else there, Matt?
No, that's great.
Okay. I've got a question here from Travis, and it says, were you able to get the data channel to work? I'm trying to now, and the Lattice FAE had to modify the IP to add the address space to the IP. Are you able to? There is one more here. I'm using it to connect the AP bus between the two FPGAs.
Yeah, so unfortunately for Travis, that was the one interface we didn't use as part of this. So the data channel is more sort of periodic memory accesses, and what we needed for video was to use the fields inside the frame that could be updated every single LTPI frame. And so that's why we chose the OEM and GPIO channels. So unfortunately, don't really have any guidance on the data channel. We did not use that as part of this demo. So yeah, go ahead, Scott. Yeah,
I would just add there, maybe we should take that one offline as well, and maybe you can connect with Travis after, Matt, and see if there's some kind of quick trial that we could do to answer some of those questions.
Sounds good. Yep, good idea.
Perfect. I'm just sending you that message, Travis, to grab your email address. Okay, question here from Mike. How did you ensure synchronization between the LTPI and MIPI clock domains when you integrated the protocols into a single design?
Yeah, I can take that one. So there's mention in the presentation about needing to use a shared reference clock just because of PLL limitations, but this question's a bit different than that. It's more, how do we pass data from one domain to the other? So and thinking of it where you're receiving MIPI RX data, even though the reference clocks might be synchronized, you're receiving data at whatever rate the sender's providing it. So you're getting video at a certain rate, and what we would do inside the design is move that into a faster clock domain. So we'd have a faster clock domain running where we're getting video data received. So not every single clock cycle, but at the rate that the video is being received. And we'd use a clock domain crossing FIFO to go from the MIPI domain to the LTPI domain. And so in both cases, the LTPI and the MIPI interfaces they're running with overhead, with room, where you're not needing to send a pixel every single clock cycle. So you have a bit of buffer. And so basically we just use the clock domain crossing FIFO, an internal buffer, to move from that MIPI domain into the other LTPI domain. And the main thing is to look at overall bandwidth. We had plenty of bandwidth on either side of that FIFO to handle the video data coming in. And so as we move across the FIFO, it would never overflow or underflow. So
Excellent. Thank you, Mike. Matt, whoever you are today. Okay, for the both of you, could you provide more detail on the tools and resources that you use during the LTPI demonstration and how developers can access them?
yeah, I can field that one as well. So we were using all the Lattice tools for this that are available through their website. So Radiant was the main tool. The other tools that we mentioned, the Reveal and Simulation Wizard, they can all be launched from Radiant. And so going through the Lattice website, there's links there to download these tools. Easy to access, easy to download. You can then go through the licensing part of their website as well to get some evaluation licenses that get you up and running quite quickly with the tools there, just to try them out. And so the licensing is all through the Lattice website as well, and accessible to everyone. So.
Excellent. Okay, so there's one last question here. So if anybody else has any more, if you want to just quickly pop them in, and then we might actually wrap it up. So to either of you, but could you elaborate on the milestone-based approach that you demonstrated and the benefits or disadvantages that it had? Challenges.
Scott, I can do a first pass, and if you want to add to it after.
Yeah, for sure.
Okay. So I think the milestone-based approach is something we feel can be applied to any project. I mean, in particularly if there's some risks and unknowns about the design. So the important part there is that we had a clear end goal for what we wanted to do. We wanted to have the LTPI, we wanted MIPI, we wanted to use the off-the-shelf hardware, but there were technical unknowns in there. We weren't really sure about some of the subtleties around the LTPI IP cores and around the MIPI cores and how we might shim them together. And you're just not able to plan a whole project from the start in the level of detail. And so you need to kind of get into it to be able to learn some of this stuff, to know how to proceed to get to your end goal. So what we looked at initially was we set the end goal, and we kind of looked at where the biggest unknowns were in terms of risks and things we weren't sure about, to plan some of the subtleties, and identified kind of, okay, like, let's get the LTPI working on its own. Let's get the MIPI working on its own. And then that information we acquire from that will allow us to know better how to shim them together. And so we set these initial goals, and I mean, it was almost like an agile workflow that we used. We used Jira to track these different milestones in there, but set an initial goal, just get something running over LTPI, get a MIPI video loop back going. What's nice about that is we could have separate people working on it in parallel. It was clear division of who was doing it, could have their own hardware doing it. And so it lends itself to kind of, sharing the work, but breaking it down into smaller chunks. And as we were going through those and learning, we started thinking about, okay, when we get these working, how are we going to combine them? And could start planning through some of that, so that when these individual parts were working, combine them, we have a better idea of how we need to shim them together. And it just becomes a lot more manageable. It avoids, trying to tackle everything at once and ending up with, nothing working in the end. It ensures you're making kind of interim process along the way. So we try to apply that to as many projects as we can, but it does take, it takes upfront work to really think through what the right milestones are and how to build up on that. So we think it's worth investing that time up front to plan it out like that, but it does take effort. It doesn't just happen. It kind of takes careful planning to be able to pick the right milestones and build up from there. So, Scott, did you have anything to add to that?
I guess the only thing that I'd add there, Matt, is as sort of the sponsor of this project, the thing that I found really, really great was the fact that the team planned that up front. And then, it came to me originally with, okay, well, we're going to need these custom boards to interface this stuff to. And I was like, okay, well, no big deal, but yeah, it takes time and it does cost a little more money. But if that's the right way to do it. But as the team understood more and more about what was how this was going to be implemented, they were able to be pretty creative about how to work around that need for custom hardware, which is fine. We can do it, but it does slow down the progress that the FPGA and software guys are trying to make. So that was one thing that I found very eye-opening on this particular undertaking was the creativity that the team used to work around the need for custom hardware, and we still were able to achieve the same result without compromise. So I guess I would encourage all of you to also okay, well, what can we do that's neat? To what kind of little boards can we get off the shelf, put them all together, and maybe do this and that, and then have the thing come together without that need for taking that extra step into custom hardware for something like this.
Excellent. Okay. Well, there's no more questions here. So it looks like we've come to the end. So I'd encourage anybody that's interested in having any of their questions asked, or any maybe confidential questions, you can reach out to our team, either by responding to the webinar recording email that will be coming out very, very shortly, including a high-res image of that block diagram for you there. And yes, please keep an eye on our webinar page. We are in our blog, subscribe to our blog, follow us on LinkedIn because we're constantly producing these tech talks at least once a month. So thank you for your time, Matt and Scott, and have a great day, everybody. Thank you.